Today we will talk about random samples and statistics. Collecting data or gathering information is an important aspect when we are doing statistics. We want to use a subset of the population to draw conclusions or inference about the entire population. This subset of interest that we use to draw inferences about the population is called a sample. The way or the process in which the sample is obtained will affect our confidence in the conclusions that we derive using it. We will work with a small example here. Let's deal with the hypothetical situation where we want to test the efficacy of a vaccine for COVID 19. Yeah, so assume we have a vaccine for COVID 19 and we are interested in knowing its efficacy. So we can consider the following experiment. Uh, the first step would be to take two samples of people, group A, group B, and the strategy might be to give the vaccine to group A. We call this the treatment arm of the experiment. And we will give the placebo to group B. We call this the control arm of the experiment. We will then expose both these groups to the virus, and the goal would be now to measure an appropriate response variable to the exposure to the virus for both of these groups. Finally, we'd want to apply some statistical tests to check if there is a statistically significant difference between the two responses, one obtained after taking the vaccine and the one without the vaccine. This is a rather simple experimental setup, and even in this case, to get correct conclusions about the efficacy of the vaccine, we would have to choose group A and B very carefully. Uh, some questions that we might be interested in would be: is it possible that certain people can never make it to either of the samples, that is, either of the groups A or B? Do your samples, that is, groups A and B, contain only young individuals, in which case you don't know how the vaccine behaves with older individuals in the population? Are your samples representative of the population? This is another way of paraphrasing point two. And finally, are the sample sizes large enough? Right? So there are multiple things going on with this experimental setup, and one of the things that we would want to deal with today is to note that many statistical tools will usually be based on principles of probability, and we would need a very precise notion of what randomness would mean in the context of choosing samples. And the goal for today would be to address this idea. We begin with the definition of a random sample. We say that x1, x2 up to xn, a set of random variables, is a random sample if it satisfies two conditions. The first condition is that all the xi's have to have the same probability distribution for I equals 1, 2, 3, all the way up to n. And the second condition for a random sample is that the set x1, x2 up through xn is an independent set of random variables. Note that sometimes a random sample would also be called as a set of independent and identically distributed random variables. This is quite a prevalent way of describing a random sample in a lot of academic literature. Okay, in short, these are called IID random variables. The common distribution of all the xi's inside a random sample is called the population distribution. So it's the distribution from which we sample. Yeah, so we're choosing a sample from a population, and the common distribution of the xi's will be the population distribution. So we have a random sample x1, x2 up to xn. This is a collection of random variables. We can now apply a sampling procedure to get small x1, x2 up to xn, which is going to be our sample data. So small x1, x2 up to xn are numbers now, and these numbers change every time we run the sampling procedure. Uh, to make this idea a little more precise, let's work out an example. Suppose we're getting a random sample of size 3 from a population that contains exactly 5 elements, that those are the numbers 1, 2, 3, 4, and 5. To get a random sample, we will need the two conditions, right? The distribution being the same, and uh, the three random variables need to be independent of each other, which means we will have to sample with replacement. Let num1, num2, and num3 be a random sample. That is, it is a collection of three random variables. Num1 samples the first number in our sample. Num2 samples the second number in the sample. And num3 is going to sample the third number inside the sample. Since we are sampling with replacement, there will be 5 to the cube ways of getting sample data, which will be of the form num1, comma num2, comma num3. So it's a 3 tuple of numbers coming from 1, 2, 3, 4, 5. Since we have 5 cubed choices of getting sample data, each run of the sampling procedure gets one of the elements inside the set which contains these 5 cubed elements, right? So it's going to be elements of the form 111, comma 112, 121, 211, all the way up to 555. So now we will use random samples to talk about statistics. So we are often interested in some features or characteristics of the random sample as opposed to elements of the random sample itself. A statistic is a quantity that is calculated using a random sample. In this context, say the random sample is the collection of random variables x1, x2 up to xn. Since the calculation of the statistic involves elements from the random sample, which are random variables, the statistic itself will end up being a random variable. What this means is that the value of the statistic will change as the sample data changes. Also, a statistic is a random variable that is defined on the sample data corresponding to a random sample. What does this mean? It means that if script x were to be the set of values of the random variables inside the random sample, uh, the sample data is going to consist of n tuples x1, x2 up through xn, where xi belongs to script x for all values of I between 1 through n. Notice that since x1, x2 up to xn is an independent set of random variables, the joint distribution for x1, x2 up to xn is going to be given by p of x1, comma x2, comma x3 up to xn equal to the product of p sub x of x1 up to p sub x of xn. And p sub x of x is the PMF of the common distribution x of all the random variables inside our random sample. We are assuming here that x is discrete. If x were to be a continuous random variable, we would use the PDF f sub x of x to define a joint PDF for the random variables x1, x2 up to xn, which lie inside our random sample. We can use the joint PMF or the joint PDF of the random variables x1 through xn to calculate the probability distribution of the statistic of interest that we're working with. This probability distribution is often called the sampling distribution of the statistic. We will be calculating a few of these in future videos. Let's revisit our example from earlier. Recall that our population was 1, 2, 3, 4, and 5, the 5 numbers. And a random sample of size 3 consisted of 3 random variables, num1, num2, and num3. Examples of statistics defined using a random sample of size 3 would be as follows. So let's have 3 columns in our table here, the name of the statistic. We will give the definition of the statistic in some numerical form. And finally, we will calculate some evaluations of the statistic on sample data. The first statistic of interest is the sample mean, which is going to be the sum of num1, num2, num3 divided by 3. This is typically denoted by x bar, and it's easy to see that the sample mean evaluated on each of these sample data is going to give us the sample mean of the sample data. For example, x bar evaluated on 4, 5, and 1 is going to be 4 plus 5 plus 1 divided by 3, which is 10 divided by 3. The next statistic would be the sample median, which is denoted by x tilde and is the median of the 3 numbers inside our random sample. For example, x tilde of 111 is going to be 1, x tilde of 333 is going to be 3, and x tilde of 154 is going to be equal to 4. The statistic sample maximum is defined as the max of num1, num2, and num3. And it's easy to see that max applied to 111 gives us 1, max applied to the sample data 125 gives us 5, and max applied to the sample data 311 will give us 3. Another statistic of interest is the sample total, which is the sum of the 3 numbers inside our sample, num1 plus num2 plus num3. And we can see that T0 applied to 111 gives us 3, T0 applied to 135 gives us 9, T0 applied to 224 gives us 8, and T0 applied to 312 gives us 3 plus 1 plus 2 equals 6. Finally, the sample variance is another example of a statistic, typically denoted by S squared, which is defined as num1 minus x bar squared plus num2 minus x bar squared plus num3 minus x bar squared divided by 2. The sample variance of 111 is calculated as 0, and the sample variance of 123 is calculated as 1 minus x bar of 123 the whole squared plus 2 minus x bar of 123 the whole squared plus 3 minus x bar of 123 the whole squared. This simplifies to minus 1 squared plus 0 squared plus 1 squared divided by 2, which is equal to 2 divided by 2 equals 1. To actually calculate the sampling distribution of each of these statistics, we would need to know the distribution of the population 1, 2, 3, 4, 5. By distribution, I mean the probability distribution of the population. We will talk about this in the next video, but for now, to briefly summarize, we have introduced the idea of a random sample, we have spoken about a statistic, and we have done a few concrete examples to get these concepts straight. This is all for now. Take care of yourselves, and I will see you around.